Now we'll work on another gas law, which is the partial pressure, and this is Dalton's law. And Dalton's law states that each gas will exert its own pressure. Okay, and so if you have a mixture of gases, then each of the gas is going to exert its own pressure. So the first problem that we are going to work on is exactly that, which is determine the partial pressures and the total pressure in a 2.5 liter container of the following gases at 15.8 degrees Celsius. Okay, and so the gases are given to us, which are two gases, 2.9 grams of helium and 1.8 grams of hydrogen. Okay, and so we have to use the formula that we've used before, PV is equal to nRT. So what we're going to do is find the pressure, okay, so which means P is equal to nRT over V. Okay, what is going to be different for this calculation is of course N, okay, because each gas is going to have its own moles. RT over V, that's going to remain the same, all right, because that's the same for both of them. The gas constant is the same. The temperature of the gas is the same, which is 15.8 degrees Celsius. And then the volume is going to be the same also, all right. So the only thing that is going to be different here for us is the number of moles. So what I'm going to do is I'm going to do the calculation for RT over V separately, and then use that to do my second calculation. Okay, and that will save me some time. But first, let's go ahead and calculate the moles. So let's do that for helium first. Okay, so for helium, 2.9 grams of helium, and convert that into moles, is 1 mole has 4.0 grams of helium, which is equal to 0.725 mole. Okay, so now if you want to plug that in the equation, at the same time, it's the same thing. So P is equal to N, which is 0.725 moles. And I'm going to write this a little bit separately from the RT over V because I want to do the separate calculation for that. Okay, and so this is still multiplied though by 0.08206, okay, liters, atmospheres over mole Kelvin. And the temperature that we have is 15.8, which remember you have to add 273 to this, and when you would do that, you will get 288.95, 0.8, and then divided by the volume, which is 2.5. Okay, so 2.5 liters. All right, so this value is going to be the same for both, all right, for helium as well as hydrogen. So I'll do a separate calculation here for this, which is then 9.48, okay, just for that. But the pressure that is exerted by helium then comes out to be 6.876 atmosphere. Okay, then we'll do the same thing for hydrogen. And we have 1.8 grams of hydrogen times 1 mole over 2 grams of hydrogen, and this is equal to 0.9 mole of hydrogen. So now pressure is equal to 0.9 mole times 9.48 coming from here. Okay, and then pressure of hydrogen gas is equal to 8.532 atmosphere. So the individual pressure exerted is this. To find the final pressure, P total, then what we have to do is P helium plus pressure of hydrogen. So 6.876 plus 8.532 atmosphere, and that is equal to 15.41 atmosphere. And you can bring it down to the right number of significant figures, which is 2 for us. Okay, so that would be about 15 atmospheres. Okay, so very simple calculation. The only thing you have to remember to do is add up all the pressures at the end, okay, after you calculate the moles. Let's work on the next one now. Here the question states a 1 liter sample of dry air at 25 degrees Celsius contains 0.0319 moles of nitrogen, 0.00856 moles of oxygen, and 0.0000381 mole argon, and of course there's some carbon dioxide. Calculate the partial pressure of nitrogen in the mixture. Okay, so we just need the partial pressure of nitrogen in this case, and so PV is equal to nRT. Okay, yet again, the number of moles of nitrogen are given to us, okay, which are right over here. So then calculating the pressure that is exerted by nitrogen is going to be equal to nRT over V. But now the number of moles that I'm going to use is only going to be for nitrogen. Okay, if I needed to find the total pressure, I would use all the moles, okay, that I needed there. But that's not what I need. I just need the number of moles of nitrogen, okay, in order to find the partial pressure of nitrogen. So then the number of moles of nitrogen are 0.0319 moles. R is 0.0821 liters atmosphere over mole Kelvin. The temperature is 25 plus 273. Again, that is 298 Kelvin. And then the volume is given to us, which is 1.00 liters. Okay, so moles, Kelvin, Kelvin is gone, liters is gone, liters is gone, and then atmosphere that we have remaining is 0.780 atmosphere. And this is just for the nitrogen now. Okay, so if you needed to find the partial pressure of oxygen, you would use the moles for oxygen. And if you need to find the total pressure, you would use the moles for each of the gases, or you can add up all the moles and then use that for N. Okay, so that is a different kind of problem. Now let's work on another problem. The third one says the main components, okay, of dry air are nitrogen, which is 78.08% nitrogen, oxygen is 20.95%, argon is 0.93%, and carbon dioxide is 0.04%. What is the partial pressure of each gas? So now we have to find the partial pressure of each gas, and the total pressure is 1 atmosphere, okay, which is supposed to be standard anyway. If you notice, in this case, we are not given any other value. So for example, we're not given the volume, we are not given temperature or anything like that. Okay, so which means that we have to solve this problem in a different way. This partial pressure problem is kind of like the mass percent. Okay, so let's set this up where we have nitrogen, and that is 78.08%, oxygen, which is 20.95%, argon is 0.93%, and carbon dioxide is 0.04%. Okay, so we're going to use this as we did for mass percents, where we changed the percents into grams. Now we're going to change the percent volume into moles. Okay, so this is percent, which means that this is equivalent to 0.7808 moles. So just convert that into moles. Okay, so 78.08 divided by 100, because this is a percent. And so that's how you would do it for all these numbers, 2095 moles of oxygen, and then 0.0093 moles for argon, and for carbon dioxide it's really a very, very small number, 0.004 moles, okay, of carbon dioxide. So that is the number of moles that we have. Since each of them exert, our totality of it, the pressure they're exerting is 1 atmosphere, just have to multiply each of this by 1 atmosphere. Yeah, really easy. Okay, 1.000 atmosphere, 1.000 atmosphere. Okay, and so therefore the pressure that is exerted by each of this is actually also equal to the moles, all right, which is 0.780 0.7808 atmosphere, 0.2095 atmosphere, 0.0093 atmosphere, and then 0.0004 atmosphere. And we could do that because these are fractions, and since we have the total amount of gases and we have the total pressure, we can use the percent, okay, as volume, and then we can use the percent as moles also. Okay, so keep it simple.